let's go to the second equation. 2a x of I plus 2b minus 2y of I equal to 0. And there's a summation involved over here. Summation involved over here for all the data points. Okay? So now let's try to make it in a matrix form. What are we solving for? A and B, because those are our unknown model parameters, right? So I'll try to put all the A terms. So what's the coefficient of A? 2xi squared. Okay. What's the coefficient of B? 2xi. So I want to put it in a matrix form.
So the power will decrease conjugated.
Okay, and let me move this because this term does not have any A or B. So let me move this to 2xi yi, correct? Okay, now let's go to the second equation. What's the coefficient of A? Because see, when I do the matrix multiplication, whatever I write over here is being multiplied by A. 2xi. What's the coefficient of this one? 2. And on the right side, what will I put? 2y. Okay, now these are summed over all data points. Let's pretend you were given 5 data points. Okay, so let me cook up an example. Suppose you were given some data points, xi, yi. Okay, suppose the data points were x of 1, yi of 2, 2.1, 2, 3.8, 4, like 7.2, something like that. Okay, let's go 6. 40. Okay, so suppose that's what the data was given to you, and your goal is to fit this data by a straight line. And so now, let me tell you how you will determine A and B. Okay, so keep in mind there's a summation over here, summation over here, summation over here. And what is the summation? This is summation over I equal to 1 to how many in our example? 4 data points, correct? So can you tell me what will be the value of 2xi squared in this example? Okay, xi is 1, 2, 4, 6. So wouldn't that be 1 square plus 2 square plus 4 square plus 6 square? Everybody agrees?
Yes.
Times 2.
Oh, times 2. Okay, what about 2xi?
So
It will
same
be-
thing, take away the squares.
Yeah, take away the square, 1 plus 2 plus 4 plus 6 times 2. Okay, same thing over here. Okay, lastly, what will I put over here?
Just 2.
No.
8.
8, because remember we are,
Oh, the length of the.
yeah, because it will be 2 plus 2 plus 2 plus 2, so it will be 8. So that's a common mistake some of you who were in the deep learning were making, just putting 2 and then the curve was not looking correct. Anyway, so if I put now A, B equal to whatever those numbers are. So again, those are also being summed over all the 4 points. So xi, yi, so this will be basically 1 into 2.1 plus 2 into 3.8, correct? And so on. And multiplied by 2. And same way you can get some data over there. We solve this So this is just a matrix with some numbers, right? So what will be A, B then?
Numbers?
Okay, whatever this is, inverse times whatever the right hand side is. Okay, so now we can easily come up with A and B and solve the problem. Okay, so this is what is called linear least squares. Okay, now in the deep learning class, one of the assignments that I gave was to do it not for a straight line, but for a second order curve. So for you guys, let me give you an assignment for a third order curve. Okay, so I'll give you so that you know if you're in deep learning, you can now get more experience with it. If you were not in deep learning, I want you to do it one time because this is a very, very important technique. Okay, you cannot claim yourself to be knowing the computer vision field if you don't know what linear least squares optimization is. Okay, so anyway, let me at least briefly show you. Okay, so suppose you are given some data. So these, actually let me do this. Okay, so you're given some data points. They're not exactly on this curve. Okay, so your goal is to come up with the equation of the curve, which will be third order, meaning x cubed. So your model will look like this: y of I equal to a xi cubed plus b xi squared plus c xi plus d. Okay, so that's what we mean. It's a third order model. You can see there's a cube term, square term, right? So your goal will be determine A, B, C, D that fits above data nicely. Okay, again in the assignment, so I'll give you some data points. I'll give you a set of data points. Okay, so there you'll be given x of yi, some number here, some number over here. So each one of these I'll give you the coordinate. Okay, now you have to go set up the math, write the code to determine A, B, C, D. Okay, so how will you do it? What will our cost function look like? Let's go. Okay, so again, it will be A xi cubed plus b squared plus c xi
plus d minus
yi
the whole square.
square
Summed
over all the data points. So how many partials will you compute now? Four. Partial L over partial A, partial L over partial B, partial L over partial C,
and
partial L over partial D. Okay, then you will compose it in a matrix form.
four cross.
So just like I showed you, you'll have a 4x4 matrix.
Yes. A, B, C, D.
A, B, C, D.
And the four
Given the data, you'll have some numbers over here.
And
And then you will do the inverse, multiply by the right side, and solve for A, B, C, D. Okay, so hopefully now you get the idea what is linear least squares optimization problem, right? So once you understand how does it work for curve fitting, now let's go apply it for images and see how can we use this technique for image registration, okay? So once again, we are given two images. And now, see here, we were just given XY data points. And we were to fit this by a curve. Here, the problem is a little bit different. The problem is we are given correspondences. So we are given basically
the location of 5.
the location of two sets of data. So we are given x1 of I, y1 of I, x2 of I, y2 of I. Okay, so for example, like I said, somebody might say this was 72, 85, this was 20, 25, and so on. So you're given some numbers, which, like, for too easy way to understand these numbers, once again, is think of it like location of the left eye, location of the right eye. It doesn't have to be eye, it could be anything. So for example, if you were given an image of a car, okay? So let's say here's a reference image of a car. Okay, as long as you know where is this point in this image. So if this is, let me make this the reference image. If this is our reference image, this is the incoming image, so somewhere over here. Okay, as long as we know where's this point over here. By the way, what technique would you use if you were to determine this point?
Oh, you mean, is that a corner detection?
Yeah, so Harris corner detection would be one possibility over here, right? So how do we determine these? Like I said, there are many different techniques. We'll answer that question later. But for right now, let's pretend we know the correspondences, right? Now set up the equation such that after we align this image, the difference between these two becomes as small as possible. So that's how we'll set up our cost function, okay? So let's set up our cost function.
Are we trying to recognize an eye? What are we, like, is the objective?
The objective is to make this look similar in shape and size as the reference image, okay? So let's say this is a picture of you in the database. Okay, perfectly straight, 100 by 100 image. You pass through a security camera. We're looking a little bit sideways. Okay. The camera has, some background and so on. Before we can do the recognition, we have to make your face similar size and shape as the reference image. Because we can't compare this with the whole thing, it will never work. So if we can locate the eyes and the nose and the chin, right? We already know where the eyes, nose, chin is, then we know the correspondences. Using correspondences, we can apply this transformation to this image so that this image becomes like this. And now we can cut it out 100 by 100, then do the matching. So this is a pre-processing step before we do the recognition. Okay.
So is there an optimal reference image size, or is it pretty relative?
You will decide, because you will be doing face recognition as we go along.
Sure.
And I'll give you the data set, and then you will decide. So typically the size is like 100 by 100 or 150 by 150. So like a relatively small face size.
Sure.
But then once you decide on that, once you do the registration, like I said, once it's been straightened, the scaling part, remember this contained the scaling. If you're referenced by 100 by 100, then you're essentially trying to make the incoming image look close to 100 by 100. Yeah. Anyway, that detail will come later.
Sure.
So let's take a look at our cost function or our loss function. So our cost function. Okay, see in the previous case, remember we determined it like this. The equation of a line minus whatever the y point is. So based on A and B, we try to minimize this error, right? Very similarly over here, the cost function will be in plain English. If we apply this transformation over here to the second image, then we compare it with the first image. We like them to be as close as possible. Okay, so basically in plain English will be let's say I1. So I1 is the incoming image. Or let me call I1 as the reference image. Okay, minus the transformation applied to I2. So this is incoming, and this is reference. So for all the correspondence points, so this is sum of our correspondences. Okay, then if we minimize the square of this, if it is as small as possible, then whatever transformation that gives us that answer is our final answer. So the unknown over here, or the model over here, is T basically. So T is the transformation. Okay, which we already had indicated what are the parameters of T.
T2.
A, B, T1, T2. So after we set it up, can you guess how many partial derivatives will we need to do? Four partial derivatives. Okay, so let's take a look at those. Okay, so now let me expand this. Okay, suppose this is x1 of I, y1 of I, minus. Okay, as I apply the transformation to A, B, minus B, A, x2 of I, y2 of I, plus t1, t2. So basically this is our transforms point, right? Sum over all the transformations square is our cost function. So this is our cost function. Everybody agrees? Apply the transformation, meaning rotation, scaling, shift to the second point, such that
And this minus will become
oh, let me put this parentheses. Right? Okay, so see the difference is previously, if you recall, there was a single equation. Okay, now as you will see, there are two equations involved. So if I expand it out, what will this look like? Summation
A square minus 2, so that will be xi minus whole square.
x1 of I minus. Now let me expand this matrix equation out. This will become A times x2 of I plus
B times
x2 of I.
y2 of I. A times x2 of I, B times y2 of I.
Y2 of I.
parentheses.
Yeah, it will be, I'll put the parentheses at the end. Okay. So as you can see, this one square. So basically I just did the top row,
Yep.
right?
Yes.
And then if I do the bottom row, this will become,
yi minus b2 x2 of
oh, I
I.
forgot the parentheses right here. Okay, so this will become
Minus b2 v y2 of I.
x2 of I, and b times
Oh yes, sir.
plus
A
a
times y2 of I
y2 of I
plus t2
plus t2,
whole square.
and the whole thing squared. So anyway, basically it reduces to basically a 2 by 1 matrix. x, right? But whenever we have a cost is a scalar, okay? Cost is not a vector. So what we can do is basically treat it as the sum of both, okay? So one easy way to do that will be do sum of x1 of I, a x2 of I plus b2 of what did I do over here? by2 of I plus t1 square plus, and let me write the second line there to make it a single cost, scalar cost function. y1 of I minus b x2 of I plus a y2 of I plus t2 squared, and sum over all the correspondence points. Okay, so this is our cost function over here, right? As we discussed, what are we trying to solve this equation for? A, B, T1, T2. So how many partials will we take? Partial C over partial A equal to 0. Partial C over partial B equal to 0. Partial C over partial T1 equal to 0. Partial C over partial T2 equal to 0. Right?
4 equation, 4 matrices.
Right. So let me just do one of these. The rest I will leave it for you to do as a homework. So C will become what? So take the 2 out over here. This will be
x1 of
1i minus a x2i plus b y2i plus t1.
into the derivative.
Okay, now take the inside derivative with respect to a.
So the first one is 0, x2 of I.
x2 of I, right?
Minus x2 of
Minus x2 of I. So let me make it minus 2. x2 of I.
I. That's right.
Okay, and then same thing we need to do with respect to a. So this will become 2 y1 of I minus b x2 of I plus a y2 of I plus t2 multiplied by the derivative with respect to a, which is y2 of I. So 2 y2 of I. Okay, and of course you'll set it to 0. So partial C over partial A. Okay, so now you'll further expand it. Put all the A terms together, you'll put all the B terms together, all the T1, so just the A and B, and you will try to express it in matrix form. Okay, so yeah, all the T1 terms together, T2 terms together, so that you can set it up as one matrix equation. So let me show it to you on my computer.
Professor,
Yes.
is there any way we can, let's say I want to build a system that I give it the order of approximation for the linear least squares, like I say 7, and he's able to do the derivatives without me doing it by hand?
Because we
Should
did
we
the
go for
math
that?
actually.
That will, I mean, if I was teaching, let's say, a different course, the only problem, I mean, you could do that. It will take you quite a bit of time to generalize it to that. Okay, because
So
there is
there's not like a function I could use?
no, because if you, for example, are you in the deep learning class?
Yes.
Or you are, right? Okay, the equation I developed over here, right? If you recall, it was like 2xi squared over here.
Yeah.
Okay, if you take a look at the third order,
So the order will keep on decreasing, right?
it was 2ix to the xi to the 4. If you go back and take a look at it, if I remember correctly,
Yeah.
same way, fourth order, you'll see. So there's a pattern to it. You can generalize it if you wanted to. Okay, but we have so many things to learn. I would rather have you know the technique, be able to do it for one case, and not spend too much energy
So,
on.
so at this point, it's compute by n and then code this. Like we are
This
doing
one
right
you
now.
have to do because this is totally different than the other one.
Oh,
Here,
because this is for, yeah.
this is for image registration. It does not follow the same pattern.
No, it doesn't, yeah, this one we have to.
You have to do all the derivatives yourself. Yeah. Okay. Anyway, let me show you on the computer how this will look like.
So you should know the math and programming, you have to be good at both, right?
Possibly.
That's the idea.
Not possibly. You have to be.
Know the right measurements. Wow.
See, like, if you play sports, let's say you play tennis or, or I know you are swimming. Okay. There's a famous saying, you're only as good as the weakest part of your game. Okay. So if you were, let's say, playing tennis and your backhand is pretty weak, you're only, that good, regardless how strong you are in the other parts. So same thing, with academics or, computer vision or deep learning. If your programming is weak or your math is weak or your general ability to be able to put it together and solve it. So I try to identify what is your weakness and work on it. Otherwise, like I said, you won't be respected if one of those things is not as strong. And everybody can become better. So just try to get that psychological fear out. Oh, I cannot program, or calculus, I did it, so anyway, so that's my recommendation. So the sports analogy, regardless is true or not, but. So do they say that in swimming or not?
Yeah. I mean, you have to always work
On your weakness, right? So just a couple of minutes.
This is the point.
Okay, so if I take you guys to the CPEG585 website. Okay, and okay, so yeah, I have not put the assignment there yet, but let me Okay, so there's a small PowerPoint that I'll put it on the website, basically explaining. Some of you who are in the deep learning have already seen this. Okay, but okay, related to image alignment, which I did not show you this part in the deep learning class. Okay, we already talked about the theory, how the transformation is computed, how one point as it's rotated, right? Here's the math for it. So okay, so anyway, this is what we talked about, right? X1, Y1 of I might be the reference image. X2 is our incoming point on the incoming image, right? So this is how we set it up. Then we assemble it into a single equation, and then we take the partial derivatives. Okay, so for example, partial C over partial A will turn out to be, as you go through the math. So I'll give you up to the first one. I won't give you the calculation of the B, calculation of the C, and so on. Okay. Anyway, so okay. So the final answer will look something to be like this, but you'll give me, I'll give you the final answer so that you know what it's supposed to be, but you'll show me how did you get there. Okay. So this is what how we'll set up to be 4x4 matrix, such that given a set of correspondences, if you were 6 correspondences were given to you, you'll sum it, exactly like we did it for the linear least squares, and invert this, multiply it by the right-hand side, and you'll be able to get the AB T1, T2 parameters, right? So then just your assignment will be, and I'll provide you with the starting code. Okay, I have to clean this a little bit, but if I run it. Okay, so anyway, suppose, and this will answer, I think one of you had asked me, how do we pick a reference image? Okay, suppose I pick this to be a reference image. Okay, so this is close to, I forgot, 100 by, maybe 80 by 100 or 80 by 105, right? So here, let me now load the second image. Okay, so suppose I pick this to be the second image. Okay. Okay, so now first, before we can apply, so the idea is rotate it, scale it, such that this face becomes same orientation and same size as the reference image, right? So first I'll show you the manual technique. In the manual technique, what I'll do is I will manually identify by clicking on the eyes, the nose, and the chin, by clicking on the eyes, nose, and the chin. So, and like I said, I'll provide this code to you.